anyhow, we can try to have a look at this task number 18, calculation of some LC filter. So we have this circuit here, some LC thing. So we have some inductance here, we have some capacitance there, and we have two resistors that are in series and in parallel to these elements. And the first task that we are going to solve is to derive the transfer function, the ratio between the output voltage that we have here to the input voltage that we have here of this filter. So, question is, how do we do this? Suggestions. So I will write output voltage divided by input voltage. Yeah, we could. So, of course, as usual in electrical engineering, you can somehow try to apply Kirchhoff's voltage law and Kirchhoff's current law to this. So we could. So what is meant here is the open circuited filter. An open circuited filter means there is no current here at the output. So the output current is zero. This is what open circuit means. And so if we have an input current, and of course we should have some input current, otherwise we don't get any useful signals here. So this means that the input current goes through this resistor, through this inductance, and then somehow also goes to this parallel circuit of the R and C here. So we have the very same circuit going through all these elements, or let's say through this resistor, inductor, and this parallel circuit here. So it's a series connection. What rule can we probably use for this series connection without having to set up really the Kirchhoff's current and voltage laws and so on? We can use a voltage divider, exactly. And so the output voltage is like the partial voltage, and the input voltage is the total voltage, the full voltage across this. So how does then the voltage divider rule work? Partial voltage divided by total voltage is exactly the partial impedance, where we have the voltage drop of this output voltage, and this is the parallel connection between R and the impedance ZC, and the total exactly is R plus ZL plus the very same parallel circuit there, R parallel to ZC. Okay. So what do you suggest to do next? I would probably try to rewrite this parallel connection. So because we have it on top and in the numerator and denominator of this fraction. So yeah, first question maybe is what is ZL and what is ZZ? ZL is J omega L and ZZ is 1 over J omega C. And so how can this parallel circuit here then be rewritten? Yeah, we could do something like 1 over R plus J omega C, which is probably not the worst choice in this case. I mean, still, it's not that nice because it's kind of a double fraction. But if we expand it with R, then we get R in the numerator, and the R here will cancel, so we get R divided by 1 plus j omega RC. Right? Or we could also write this parallel circuit as the product of the impedances, R times 1 over j omega C, divided by the sum of the two impedances, R plus 1 over j omega C. And so then if we would take this double fraction and expand it with j omega C, then we would cancel it here, we would cancel it there, and we would also add it 1 times there. So at the end we end up with the very same expression for this. As said, unfortunately my highlighting does not really work today. Okay, so now we can like take this, and it's even sometimes difficult to find for me where my pen is. So we can take this and insert it here and insert it there into our voltage divider rule. So yeah, then we get R divided by 1 plus j omega RC, and a quite long fraction bar. And in the denominator, we have R plus j omega L plus the same expression as before, R divided by 1 plus j omega RC. Okay. In general, I would say we would be more or less finished. Yeah? We have some expression that depends on R, L, C, and omega, or angular frequency omega. But of course, we would maybe like to rewrite this in a nicer, more simple, more understandable way. So what would you suggest to do? Any ideas? Double fractions are usually bad. No one likes double fractions, so let's try to get rid of this double fraction. So once again, let's expand with this term here. Let's try to get rid of this. So we multiply here with this, we multiply here with this, so then it's gone here and there. And let me also, yeah, no, not delete the plus there. Of course, what is left then here on the top is R. What is left here is also R. But here for this term, we add this. We multiply with 1 plus j omega RC exactly. So do I have enough space to write? No, probably I will continue here. So we have R in the numerator, and then we get R plus j omega L multiplied with 1 plus j omega RC plus R. Okay, it's maybe getting nicer. So one last thing that we could probably do is, so we have a 1 here at this position. Here where this R is, let's also try to get a 1 here. Yeah, and we have some R here and some R there. So what I would suggest is to divide by R. So divide by R in the numerator, then we get some 1 left. And in the denominator, we have two parts of a sum. And so in each part, we have to divide by R. So if we divide by R here, we are left with a 1. And so here, we have a product of two factors. If we divide by R in one of these factors, we need to divide by R. So let's divide here by R. So then we get some 1 here, and we also divide by R here at this position. And so then what we are left with is a 1 divided by 1 plus J omega L divided by R. It's a double fraction, but it's not too bad in this case. And 1 plus J omega RC. And another 1. And this is now not looking too bad, because we have lots of 1s, and each parameter only appears once. Yeah, we just have the L once and the C once. Okay, and the R we have twice, but yeah, 1 R, to be honest, is the first R, which is, I don't know, somewhere here. Right, we don't have labeled them as R1 and R2, but one of these R's would be the first R, one of these R's would be the second R. Hopefully. Okay, so what we can do now, and I will try to copy this here and put it onto the next page. So what we can try to do with this, and this was our ratio between the output voltage to the input voltage. We can introduce 2 new variables and say this here is a first corner frequency, omega C1, and this is R divided by L. And this here we rewrite as a second corner frequency, omega C2, and it's 1 over RC. And we could check that, and at first, okay, let's maybe rewrite our transfer function, because then it gets even simpler. So we have 1 plus J omega divided by the first corner frequency, multiplied with 1 plus J omega divided by the second corner frequency plus 1. And so if we maybe check the units of these corner frequencies, to check if they are really frequencies, what is the unit of the resistance? Ohm, and ohm can be written as volt divided by ampere, exactly. And so then we have inductance, the unit of the inductance is Henry, and Henry can be written as no, not really. So, I mean, we could also do it backwards. What unit would we would like to have for some angular frequency? So ohm is volt divided by ampere, and Henry. So for the corner frequency, what is the unit of a frequency? Hertz, or 1 over second. Right, so we would like to have 1 over second here, and the volt needs to cancel and the ampere needs to cancel. Exactly, and so that's why Henry is the same as volt second divided by ampere. Right, and then the volts will cancel each other, the amperes will cancel each other, and we have what is left is 1 over second, which perfectly makes sense. And the second corner frequency, we can also check. We have 1 over ohm. Ohm was volt divided by ampere. And then we have, what is the unit of the capacitance? Farad, exactly. And farad can be rewritten as I mean, it's the same here. We would like to have 1/2 at the end, but the ampere needs to be gone and the volt needs to be gone. Exactly. So we need ampere second per volt. Charge divided by the voltage that created this charge. And so volts and ampere will cancel each other. We get 1/2, which also makes perfect sense for this second corner frequency. Okay. So then, yeah, we can maybe go back to task, because I would say this is now what we have fulfilled. We have derived this transfer function here for the open circuit filter in the frequency domain, and we've introduced some 2 corner frequencies. Then the next step in task B is to draw this as some attenuation, and the attenuation is the reciprocal fraction, the input voltage divided by the output voltage, and then just the magnitude of this for a frequency range from 10 kilohertz to 100 megahertz. And there are some values given. So we have some resistance here, 50 ohm. We have some inductance, 10 microhenry, and we have some 10 nanofarad of capacitance. And there is some anti-diagram mentioned in figure 1. So I can try to find this anti-diagram. Is here. If I go to full screen in my browser, then I probably see the full diagram. Wait, this is the Hint tool. Okay. So let's copy this into my drawing program on a new page. Maybe here. And so we can now into this diagram try to draw the amplitude response of our filter. And I will, yeah, maybe copy this, or not copy this. If we take the inverse, if we take the reciprocal value of this, then we just get this term, right? Just the denominator. So what we are interested now in this attenuation is the attenuation is the magnitude of what we had before, 1 plus j omega divided by omega C1 multiplied with 1 plus j omega divided by the second corner frequency C2, and then plus 1. And we would like to convert this into a dB scale. Okay, so what do you suggest to do to draw this? And I mean, the first thing that we can maybe do is we can calculate these corner frequencies. So we have some resistance here and some inductance. So from these 2 values, 50 ohm and 10 microhenry, we can calculate this first corner frequency. Maybe I can write this here. So omega C1 is 50 ohm divided by 10 microhenry. And so we already checked that the units would be second. And yeah, so the value micro is, what does micro mean? 10 to the power of minus 6. So 10 to the power of minus 6 below the fraction bar can be also written as 10 to the power of 6 above the fraction bar. And then we have 50 divided by 10 is 5. So we get 5 times 10 to the power of 6 1/2. And the same way we can also calculate the second corner frequency. It was 1/R. R here in this case is also 50 ohm, and the capacitance was or is 10 nanofarad. So okay, then do the 10 nanofarad there. So we already checked that ohm and farad will also give 1/2. Nano means 10 to the power of minus 9. That I can also write as 10 to the power of plus 9 above the fraction bar. And so 50 times 10 is 500. And so we have, or maybe I could also write this here as 10 to the power of 2 and then delete your 2. And so we have 1/5 is 0.2. So we get exactly 0.2 times 10 to the power of 7. And so this is the same as 2 times 10 to the power of 6. And here the 1/2 is missing 1/2. So we have 5 and 2 times 10 to the power of 6 as these two corner frequencies. And they are quite close together. Okay, so now going back to our diagram here. So we now know values for these corner frequencies. So in our function here, for this corner frequency and for this corner frequency, now we know some value. So what do you suggest next to calculate to finally draw this function? Say again? Yeah, so of course we have some frequency range here. And of course our omega is 2 times P times F. And so the frequency range is given here, and this is, as mentioned, from 10 kilohertz up to 100 megahertz. And okay, so from this may be a good and interesting step. So from our two corner frequencies that we have, we could calculate the corresponding, or I mean, these are angular frequencies. From these angular frequencies, we could calculate the usual frequencies. So we take the corner frequencies and we divide by 2p. And so difficult to do this by head, but 2p is approximately 6. If we divide 5 by 6, we get something like 0.8, I would say, megahertz. That's 0.795. Something like this, right? Only 17. Okay.
Yeah, maybe I approximate that.
Okay. Okay. 0.79 megahertz. And so the second one, 2 divided by 6 is 0.31, but 0.0318, right? No, I know, no, it's not 0. I mean, we have the 2 here, so it's 0. No, what did you say? 6, 7?
3, 1.
3, 1. Okay. Yeah, this makes sense. Okay. Yeah, I mean, it should be still the same ratio between the two. So this is like 2 to 5 to 2. And so this is also, yeah, it's really challenging to find my pin here. So from here to here, we divide by 2.5. And so also from here to here, we divide by 2.5. Right? Yes. Okay. So these two corner frequencies, 0.8, let's say 0.8 and 0.3 megahertz, they are somewhere here in this range. Somewhere around the 1 megahertz here in the center of this diagram. So, somewhere here. So it might be interesting to take a look at what happens for frequencies, what happens to this A, how can we approximate this A if we have frequencies that are much smaller than these corner frequencies. And for sure, it would be interesting to approximate this A for frequencies that are larger or much larger than these corner frequencies. So if we do the first thing, if we look at this A, if the frequency, does not matter if it's the frequency or the corner frequency, if now this angular frequency is much smaller than this angular frequency, and if this angular frequency is much smaller than this angular frequency. So what happens? So in this case, we can neglect this term because this will be small in comparison with the 1. This will be also small. I could say this goes to 0, this goes to 0 in this case. So we have 1 multiplied with 1 plus 1. So it's 2. So our factor there, our attenuation of the filter is 2. And if we convert this into dB, what does it mean? What is a factor of 2 in dB? No, 10 means factor of 10 for power quantities, factor of square root of 10 for root power quantities. Or how could we calculate it? How can we convert this factor of 2 into dB? Yeah, 20 and which log? Yeah, the decadic logarithm of this factor of 2. And if we do this, we would end up with approximately 6 dB. Okay. So then let's go for the next case where these frequencies, corner frequencies, angular frequencies are much larger than the corner frequencies. So if this term grows large in comparison with 1, if this term here also grows large in comparison with the 1, what happens?
So we also think this like a link with the frequency that is gain QC.
Yeah, exactly. It's like frequency, a little bit like frequency is going to infinity. So in this case, you can neglect the 1 because the 1 is smaller than the other term, and we can neglect this one because it's smaller than the other term. And if these two are large, and if the product of them is also large, then we can also neglect this one here at the end. So finally, we get something that looks like, yeah, and so then what you have also left is j times j. So j times j is -1, but if we just take the magnitude, we don't care. Yeah, so we can also neglect the j in this case. Okay, so we get omega divided by omega c1 multiplied with omega divided by omega c2. And yeah, so we get something that grows proportional to the square of the frequency, because I could cancel 1 omega here and write omega square. And so if we convert this into dB, once again, if we in this case write A in dB is 20 times this decadic logarithm of omega square divided by omega c1 times omega c2. Yeah, what could I possibly do with this to simplify it a little bit? Yeah, take the 2 out and move this 2 to the front. And so then we get 40 dB. I would probably rather write it like this to say, so then we get 40 dB per decade. You get 40 dB increase of our attenuation per frequency decay. And yeah, and that's probably it. So now this means that, yeah, okay, and we have these 2 corner frequencies here that are still somehow left. And so we have like the product of the 2 corner frequencies. And if we take the square here out, then what would be interesting next would be is, I think I have some space here to write, would be what is omega c1 multiplied with omega c2 and then the square root of this, right? Because if we take the square out on the top, we also need to take the square out in the bottom. And so if we go back to our values here, the one was 5 and the other one was 2. So 2 times 5 is 10, and the square root of 10 is approximately 3, right? Okay, so square root of this is approximately 3 times 10 to the power of 6, 1 over second. And this means, this is all going horribly wrong here. The program. 3 times 10 to the power of not minus but plus 6, 1 over second. And if we convert this into a frequency, so I don't know, call this just omega c. So if omega c12, if we calculate the corresponding, yeah, so now we have 3 divided by 2p, right? We take this, divide by 2p. 2p is approximately 6. Once again, 3 divided by 6 is 0.5. And so we get a little less than 0.5. We get 0.47 megahertz. But I mean, we cannot really draw and plot 0.47. We can plot 0.5 megahertz. Okay, so our corner frequency, so here's 0.1, 0.2, 0.3, 4, and 5. Here's where our corner frequency is. Here's where this FC12 is. And so above this, we know that it's increasing with 40 dB per decade. And it's starting from this value of 0. So after another frequency decade, so here would be 2, 3, 4, 5. So here's one frequency decade. We already increased by 40 dB. So we are there. And so here's 2, 3, 4, 5. Here's another frequency decade. Here's 40 dB. Here would be 80 dB. And so we get, for the high frequency behavior, we get a line that should look like this. Okay, so we can go back to our low frequency behavior that we had here. This 6 dB. And so the 6 dB would be just somewhere here. So the 6 dB is somewhere here. And so I think now the line moved a little bit because it's not really on top of this diagram anymore. So let me redraw this line. So 6 dB should be somewhere here, but I think it's still somehow wrong, but you get the idea, right? So we have something like 6 dB here up to this corner frequency. Then we have, two corner frequencies, one corner frequency after which the attenuation would increase with just 20 dB per decade. And after this, it increases with 40 dB per decade. But because our two corner frequencies are so close together, they look like just one corner frequency, let's say. And after this, the attenuation goes up with the 40 dB per decade. There's a question.
I didn't understand why you marked the frequency at 850 kg.
Because this is one frequency decade. So our corner frequency is at 0.5.
Okay.
And so if we increase, let me try to re-get this formulas here. So, and if we increase the frequency, so somewhere here, if it's broken, it's broken. Sometimes you have bad luck. So if we increase the frequency inside the logarithm by a factor of 10, the decadic logarithm of 10 is 1. And so we get another 20 or we get another 40 dB in this case. So every frequency decade, you get 40 dB more of attenuation for this filter. And because it's a second order filter, because we have two different elements in there, some L and some C. And so we can shortly discuss, before we think about what this last task does, we can shortly think about what type of filter is it and why does it work like this? Well, wait. The thing is that what we have drawn now is the attenuation. And so the attenuation means now what we have drawn is it's small for low frequencies. Now the plot looks good once again, So it's small for low frequencies and then it increases for higher frequencies. I have some idea. Let me quickly change one of these markers to something that is super thick. So then, you always need to have a workaround. Okay, so, so at low frequencies, the attenuation is small, and for high frequencies, it increases. And so that's why it's a low-pass filter. And this also makes sense in a way that for small frequencies, the impedance of the inductor is small because the impedance is j omega L. If we have small angular frequency, then it says small impedance. So low frequencies can get through, but the higher the frequency, the higher the impedance of this inductor, so higher frequencies get attenuated. And so then we have this capacitor here, and the impedance of the capacitor has the reciprocal behavior. So for small frequencies, 1 over something small is something large. So for small frequencies, we have a large impedance. Current needs to go this way. But for high frequencies, 1 over something high is something small. So for high frequencies, this is like a short circuit to ground. So high frequency currents that would somehow pass this inductor would be dissipated over this capacitor and return via ground back to the source. Right? But this only really works if our source impedance if our generator impedance would be a rather small impedance, because this high impedance can only be effective if we have a small source impedance. If the source impedance is already high, okay, then we have another high impedance, nothing would really happen. So the inductor in this case makes sense if we have a small source impedance, and the capacitor like this makes sense if we have a rather high load impedance. Because if you would have a small load impedance, and then you have another small impedance in parallel, nothing would really change. So this behavior of L and C makes sense if, let's write this down, if our Z1 is rather small, and if our Z2, whatever is connected here, is rather large or is going to infinity, right? Then that makes sense in this case. Okay. Further questions? Then let's try to think about task C. And then we might have a quick break. So in task C, the question is, how does the result change if we take some parasitic capacitance into account between the windings of the inductor? Because this inductor is a coil, it's made out of a wire, and there will be some parasitic capacitance between these wires. And so we can assume some parallel capacitance to this inductor. Let me draw this capacitance. So we would have some additional parasitic capacitance here. So yeah, what would change? If we take a look at our equations, what would change? Exactly. So in our ZL would change into something ZL parallel to this parasitic capacitance. And so so then we can check. Here still we have this J omega L. So here also this J omega L would turn into this parallel circuit. So let me another time try to copy this one here and go to the last page and paste it here. So in task, what was the C or D? It was C. So in C, this ratio output voltage to input voltage, instead of this L here, now we need to have some ZL parallel to the ZZ of this parasitic capacitor. So once again, how can I write this parallel circuit? For example, as product of the impedances divided by the sum. So we have j omega L multiplied with 1 over j omega C parallel, and then j omega L plus 1 over j C parallel or parasitic, or whatever this means. So how to simplify this this expression? You can once again expand by this. So we will cancel it here and cancel it there, and then we need to add it here. J omega C parallel. So we get j omega L divided by 1. So, and then j times j, as already discussed, is minus j omega squared L C parallel, something like this, maybe, right? Okay, and so now we can take this expression. Yeah, and I have to remove also the j omega from there, right? Because we express j omega. So I can copy and say there is 1 plus, oh no, 1 divided by 1 plus, now this term, j omega L divided by R, what we had before, but now divided by 1 minus j omega square L C parallel. And then I can just copy what we had before. So 1 plus j omega RC plus 1 at the end. Okay. Yes.
Is 12 equals minus 1 here? Why we write j?
Yeah. Very good point. So the j is of course wrong. There's no j anymore. The j turned into the minus 1. The j squared turned into the minus 1. Very good point. Okay. So now we can have a look at this, at this new equation, and could once again discuss what would be our behavior of the attenuation if the frequency, let's say, goes to 0, or if the frequency is very small, if it's smaller than the corner frequencies. So in this case, omega is getting small, we just divide by 1. Omega is small, something small divided by 1 is something small, so everything as before. This would be 2, this would be 2, and this would correspond to the 6 dB that we had before. So, but if we go to the high frequency case, if omega is going to infinity, or if omega is higher than our break frequencies, so here it's the same as before, but what happens here? If omega is getting high, then this is growing large, so we can neglect the 1 in comparison, and omega divided by omega square will get 0. So we have 1 plus or minus 0 is 1. So we have, and 1 times this remaining term is this remaining term. So we get something that is just proportional to omega. So we get something like omega divided by omega C. I don't know what this corner frequency here was. It was the second one. I think so. Yeah, so we just get this. And so this means this corresponds just to a 20 dB increase per decade. So at least for the very high frequencies. And so in between something happens, and this is maybe what we could still calculate by hand is, of course, something interesting happens here if this fraction is getting 0. Because if this is getting 0, what would happen? Yeah, the whole thing goes to infinity, and if we have like 1 over infinity is also getting very small, or our attenuation would get very high in this case. So would be interesting to check, you know, when this is approximately 0. And so this would mean that omega square is the same as 1 over LC parallel. And yeah, so omega would be square root of this. And so on, we can just insert the values and say it 1 over the inductance was 10 times 10 to the power of -6 Henry, and is parasitic parallel capacitance, if we check the TARS, was 1.25 picofarads. So 1.2 what 1.25 something is done. 1.25 is, yeah, and so, and pico means 10 to the power of -12. Okay, and Henry is volt seconds per ampere. Farad is ampere second per volt. So the amperes will cancel each other, the volts will cancel each other. We just get seconds square left, and the square root of second square will be second, 1 over second, which makes sense. And yeah, so it's probably the simplest thing to just calculate this using a calculator, but I mean, we have 10 to the power of -6 and 10 to the power of -12, so this would be 10 to the power of 18 in the numerator. And the square root of this would be 10 to the power of 9, which somehow makes sense. And then we have 10 and 1.25, which would be 12.5, and 1 over 12 is 0.08 something, and we have 1 over second square. And yeah, so maybe I should better write some approximate here at this position. Do you have something calculated?
Yes.
Do you have something
2.8 10 to the power of 8.
2.8 times 10 to the power of 8. This is still angular frequency, right?
Yes.
Yeah. 1 over second. And now we can convert this into a frequency.
I converted, but I checked it's 45 megahertz.
It's 45 megahertz. So this corresponds to 45 megahertz of, let's say, usual frequency, right? Because this is something like 280, and 280 divided by 6 is 45. Okay. So this means that at 45 megahertz, which would be somewhere here. So here is 10, 20, 30, 40. At 45, somewhere here, we would get a very high attenuation. And above this, the attenuation is getting smaller once again and only increases with 20 dB per decade. starting from our corner frequency, right? And 20 dB curly Kate would be somewhere here and would be somewhere there, and so then continue like this. So we would, for the very high frequencies, we would get something like this. And so at this particular frequency here, we get something very high. So our new attenuation curve for the C case would look like this, that it's staying constant, then it's increasing like before, then it's really increasing a lot, and then it would go down again and would somehow approximate this curve. This is what we would get in task C. Questions so far? Sure. The bottom left part. This one here. Okay, because here we said our frequencies or our angular frequencies goes to infinity. So if the frequency here grows large, it's getting this term, the second term here in the denominator is getting larger than the 1. So we can neglect the 1. So, but then we have omega divided by omega square. So both grow, but the denominator grows larger, grows faster. So this fraction then will still go to 0. And so 1 plus 0 is 1, and 1 times this is the remaining term. And I mean, here in the second case, we can still neglect the 1. Yeah, so in this case, we can neglect the 1 at first, but then we can neglect this whole term. And so what is left is 1 times j omega RC, and RC was the same as 1 over the second corner frequency. And that's why we get this term here from this case. And we only get this 20 dB increase per decade anymore.